Hello and welcome again to the Theories of Everything program. I'm David Tower. Viewers, this is the first program in our new big picture series, Theories of Time. Time is pervasive, it is everywhere in our lives, it is everywhere in the universe. And it's been and still is one of the hardest concepts for philosophers and scientists to understand, to comprehend, to sort of tease out, because time seems to be entwined in everything. It's in our mind, for example, when we categorise moments in time as the past and the present or the now and the future. Actually, we're living primarily in that instance in the future, because all our planning, all our next movements, what we're going to eat, where we're going to walk, what we're going to do and say, what we're going to do in a week's time, what we're going to do in 5 years' time, how we're going to plan our lives in the future, everything takes place in our mind in the future. And we draw on the past, we draw on our memories, we draw on our history and the history of others to understand and create that future, to take the best path to that future. We realise that in the now, in the present, there's a series of instants, like a series of snapshots, a series of frames in a film. But actually we're living primarily in the future constantly. We'll come back to that in one of our future programs, how the mind conceptualises and blends and copes with time itself. And then we have it in our body clocks. We have time built into us biologically because we're geared to the seasons. Early hunters, early humans, when they stopped hunting and scavenging and settled down to farm, they had to work out how those seasons would affect the growing patterns of plants. They also learnt to understand the stars so that they could navigate by those stars, the cycles of the stars. And they also learnt that day and night controlled everything they did. The amount of sleep they had, when they'd wake in the morning, the sun, the timing of the cycle of the sun would control everything in their lives biologically, and still does. And again, we'll talk about that more in a future program. And then, of course, viewers, time is with us in the form of change. The sequence of events, the distance between events, the flow of events, just as it's with us in the flow from our birth to our death. It's with us constantly in the way everything changes in the universe, because everything in the universe not only changes, it evolves. There is a constant process of change, and that we measure by time constantly. And it was Newton that really pinned this down. He related the change in momentum of a body, or the change of velocity, in terms of the force acting on it. And to do that he had to invent the calculus. And that really brought into our concept the notion of an infinitesimal slice of time, so that change could be measured from one tiny instant to another. And he developed the calculus to do that, and from that, of course, he developed his law of gravitation. And many others were involved as well, many other mathematicians, in refining these notions of time in mathematics. But these laws also, these classical laws of force and acceleration and mass, regard time really as fairly arbitrary. In other words, if you exchange negative time for positive time, it doesn't change the laws. Doesn't change the laws of nature, the laws of physics in classical terms. So it's just as easy to go backwards in time as forward in time in terms of these equations that affect bodies, particles, masses, accelerations, etc. And remember, time is also a trap if you're trying to pin it down, if you're trying to sort of flush it out, as thousands of philosophers and scientists have tried to do since the beginning of time. In fact, it's a trap to think of it only in terms of periodic cycles as measured by clocks, for example, or as measured by the rotation of the Earth, or the rotation of the Earth around the Sun. Any period that can be measured is extraordinarily useful for humans in their day-to-day civilization and technology, but it doesn't really get to the heart of what time is. It's a measure of it, one measure of it. So if you have a pendulum swinging, that periodic cycle can be used to measure the duration of events. if you have a watch that's run by a spring, the tiny wheel oscillating backwards and forwards inside it, driven by a spring, that, the energy of a spring, that is another form of periodic cycle which can measure more accurately than a pendulum. Then you come, the next breakthrough in measuring these periods of time came in the form of a quartz oscillator. A quartz crystal, a piezoelectric effect that when voltage is applied, it causes oscillations to occur in that crystal, and those oscillations can be picked up and create a time period, a time measurement. And then because more and more accuracy was required in our day-to-day technology, an even better mechanism of measuring a period was developed, the atomic clock, the oscillation between energy levels in a particular atom was able to be measured, and that pins the period of time down to 1 nanosecond, an accuracy of 1 nanosecond per year. But again, these are just measures, these aren't time. These measures of time, these metrics, no matter how accurate, don't tell us really what time is. Also, Newton's concept of time not only really disregards whether it's positive or negative, but it really puts space and time on a pedestal as a grand backdrop, going from eternity in the past to eternity in the future. Much the same as many early cosmogonies. Theories of cosmology were developed by early humans. That grand backdrop, that grand stage against which everything else is played out. And still, we tend to think of time a little like that, in Newtonian terms, in Platonic terms, if you like. And in fact, there's a new theory that develops that concept a little further. But space and time, if you consider them separately, if you consider them as a backdrop only, it limits our ability to go further, to understand further. And the person that had most to do with a greater understanding, a widening of our understanding of time, was of course Einstein. Now viewers, whereas Newton said that space and time are immutable, never changed, and would always be the same regardless of who was observing or measuring space and time, Einstein said something quite radically different. Einstein said that time was related to the reference frame of the observer, the difference between the observer's reference frame and the object or event that was being observed. And the reason Einstein could say that was because the speed of light has been found to be constant. It's been measured many times, it's been tested. In this epoch anyway, it's always been around 300,000 kilometres per second. There is some theories that say that the speed of light may have varied in the early stages soon after the Big Bang, but that's still being tested. But in present times, the speed of light has always been that constant. No matter how fast the observer is going, the observer can never catch or change a light wave. It'll always be ahead no matter how fast that observer goes. The light will always continue to be measured at 300,000 kilometres per second ahead of the motion of the observer. But when the observer is moving very fast, of course, it changes the sequence of events. Two events which appear simultaneous, to occur simultaneously to an observer when the observer is stationary, may appear to be operating separately, to come into being separately when the observer is in motion, particularly if the observer is moving very fast. And it changes everything beyond that. It changes time, because when the observer speeds up and tries to chase the speed of light or tries to reach the speed of light, time slows down. Every cell in the observer's body, the metabolic rate slows down. If the observer has a clock, the clock slows down because it's a physical process. We can say that time slows down. That's not quite accurate. It's the time as measured by the body clocks and the physical clocks of the observer's frame of reference that slows down. But that's how we talk about time anyway in our day-to-day life. In other words, if you send that observer off into space at nearly the speed of light, he will age, and he's away for a year in his time. He will age 1 year of time. To the person back on Earth, though, who has aged 10 years in that time, probably, in their time, this person has come back into their future. The person who's been stationary on Earth has aged 10 years. The person who's speeded up towards the speed of light has only aged 1 year. So that's one way of going back to the future. But Einstein realised that time wasn't a constant, time would vary, and also the length of an object would contract as it speeds up, and also its mass gets greater. So this was the initial theory of relativity, the initial theory of special relativity. It allowed the observer's frame to be changed and measured and related. The laws of physics didn't change, but the measurement of the objects within those affected by those laws did change. Length and time and mass, etc. But Einstein did a lot more than that. Einstein rolled space and time into one. In his general theory of relativity, particularly, this became absolutely vital to understand a new law of gravity, a new concept of gravity. While Newton's laws still measured gravity accurately between two bodies, Einstein showed how gravity worked, what it was. It was the impact of mass and energy on space-time. It distorted space-time. The larger the object, the more the distortion, the greater the gravity. And Einstein's laws, Einstein's gravitational laws, did just that. They measured the impact of a mass on the curvature of space-time. Now that means that time, by rolling time up with space, 3 dimensions of space, 1 dimension of time, but rolling them together, and in fact being able to make time actually a 4th dimension of space, had a massive effect on our understanding. It's as if you've got 3-dimensional space in time slices. And everyone knows that if you give someone directions, if you give someone instructions on where to meet, on how to meet, you want to meet someone, you don't just tell them their spatial coordinates. Outside the post office, you've got to tell them a time coordinate as well. And again, you can measure space in terms of time then, because of the constant speed of light. You can say it's 1/300th millionth of a second, basically. That's the length that light will travel in that fraction, that tiny fraction of a second. It's a much more accurate way of measuring length in terms of time than trying to measure it any other way. Remember that Riemann was the first to be able to get away from the Euclidean type of geometry, to be able to provide a measure of curved space. And that's what Einstein applied in his equations. And because that curvature is measured in terms of spatial and time dimensions rolled together, 4D space-time, that brings time very much into the equation of mass and energy and everything in the universe. Suddenly time is not a distant backdrop, a constant backdrop. It is causing the evolution of space-time. It is involved in the evolution, intimately involved in the evolution of the universe. So viewers, now that we understand that time is intimately involved with the evolution of the universe, in terms of this 4-dimensional space-time creation, which is constantly evolving according to the mass and energy in it, and the mass and energy is evolving according to the distortion of space-time as well. No backdrop, that's it, basically. It's background independent, if you like. It's not dependent on having something immutable there. It's actually it. It's this constant evolution. Now that we understand that, and it's taken a long time, then we can go back and look at the beginning of the universe. If it's part of the universe, it must have been part of the beginning, when space and time emerged, the universe was created. There are lots of theories about the early creation of the universe. And they agree often with the early conceptualizations of early peoples, early cosmogonies, that said when the world was created, when the universe was created, time was created at the same time. There was nothing really before it. There's just this eternity. And you can look on the creation of the universe in just that way. And according to Einstein's equation, it was created at a point in time, a singularity, just like there's a singularity inside a black hole. Space is distorted so much, it curls up into an infinitely small space called a singularity. Now, that doesn't quite do the job, because it's possible, it's necessary in fact, to reconcile what happens at the very tiny level, at the atomic level, with what happens at the vast cosmological level, at Einstein's level. So bringing quantum mechanics together with, and at the same time bringing space and time together in quantum mechanics with Einstein's space-time, is the most important task facing physicists today. Quantum theories of gravity, bringing those two things together, the very large and the very small. And at the instant the universe was created, through a massive explosion of energy, perhaps changing the dimensions of space-time from 10 or 11 down to 3, plus 1 again, 4 dimensions, the others curling up. Whether it came out of a black hole, whether it came out of some other mechanism, at that point there may be no specific boundary. A no-boundary proposal has been proposed, where basically at that instant time doesn't really exist, just spatial paths exist. There's no sharp point at the beginning, there's a curve. And basically the universe tunnels out of nothing. It tunnels through in a quantum mechanical way, according to quantum physics, and bursts into existence. But at that point in time, there is no time. Time emerges an instant later. So the birth of the universe is roughly equated to the birth of time, or in our universe anyway. There may have been other times in other universes, and there no doubt were, and we'll discuss that again in a future program in this series. But basically, that is how time and space has been reconciled at the beginning of our universe by physicists. Now, talking about creation, the instant of creation, of course everyone's heard of the Big Bang Theory. The Big Bang Theory creating, again, our universe in an instant, going through a huge inflationary process, expanding very quickly and then continuing to expand. That's not the only theory about the creation of the universe. Another theory is the cyclic universe, where our universe can be considered as a three-dimensional universe, a four-dimensional universe sitting on within a five-dimensional structure. It's sitting on in terms of a membrane, if you like, a four-dimensional membrane in a five-dimensional space. And the clash of universes on these membranes create the Big Bang, create the beginning of our universe. But it's a cyclic process. It's also a major theory which can be tested in a few years' time, because it doesn't require gravitational waves. So basically this eternal cycle of acting as the vacuum acting as a spring, in other words, stretching initially, creating a new universe, then coming back again. And then another clash, and then another creation event, and then coming back again, and so on. This also really creates time in a more timeless way. As I said before, you can look at the before time rather than just looking at time coming into being in our universe. You can look at time as a part of an ongoing, infinite, eternal process, not separate, still bound up with space, time, mass, energy and everything, but going on forever. And now, viewers, we come to the really, really interesting part of our understanding of time. And this formulation of new ideas has only occurred very recently, in the last few years in fact. There's been a number of contenders. There's been a new one on the block, a new kid on the block that's called Platonia. It goes back to that Platonic eternal universe, but not quite the same as as Newton's. It says basically that every possible configuration of time and space exists now. And really, our history is just a series of frozen snapshots. In other words, the snapshots could be of me at this instant with certain memories in a certain place and time. And the next one could be the next stage and the next stage, but a series of nows. No future, no past, just a constant series of nows, and not so much a progression from one now to the next, but a number of nows almost simultaneously, so we get the impression, the illusion that time is flowing, but it's not really. It's just a series of frozen snapshots with the events actually occurring to us as the most probable ones in this vast universe of frozen time. And then there's the old theory of the flow of time, the arrow of time theory, which we haven't mentioned yet, which talks about increase in disorder over time. It talks about the phenomena of entropy, which is the number of possible states that a system can exist in, and over time it gets more disordered. From a very simple beginning, the Big Bang, over time it spreads out. And eventually you go from, if you like, a hot period, you bring temperature into this. Entropy can be measured in terms of energy as well as in terms of information. Two ways of looking at entropy. But the entropy always never decreases. It always increases, except in small pockets, which is you and I and the planets, etc. But overall, it increases. We use up energy over time. It becomes more disordered, our universe, and eventually it dies. There's an arrow there, a thermodynamics arrow of time, if you like, an entropic arrow of time. There is a progression from order to disorder, but that's a bit of an illusion, and we may come back to that again in one of these future programs in this series. But the really exciting news, the really exciting theory in the last couple of years is based on what's called causal set theory. It basically says that, we've discussed it before as loop quantum gravity, that underneath all mass, etc., exists information, and information exists at a grainy level, at a quantisized level. In other words, in little packets of space and time joined up, and information flows. And what this theory says very quickly is that space-time grows. New packets of space-time information, if you like, are continuously added, and this gels with our own notion of the flow of space and time in our mind. Again, we'll discuss that in the third program. We understand intrinsically that there's a flow of time going on in our lives, and for the first time there's a theory that says yes, there is a flow, there's a continuous increase in these little packets of information and energy over time, over a period, and basically time is the relationships between these events. It's a causal relationship. If I cause something to happen, what I cause to happen must happen after the cause, after I do something or say something or throw a ball, whatever, and I hit a pane of glass, it'll break. Time is measured in the relationships between the cause and the effect, and these are continuously growing and creating space-time as they increase in number. Starting out very simply, that they get new ancestors. It's like having a number of parents and creating a child constantly. It grows, it flows. And this is the latest theory of time. It's a causal effect. Something causes something, and that is the essence of time. So it's not just change, not just evolution. It's actually this connection between the past and the future. I'm David Tao, and you've been watching the Theories of Everything program again. I'll look forward to seeing you again next week.